Well, we don't really know. So if you access here, don't get valid. The only place conventional storage flow is actually correct. It is dead. The current flow is actually positive charge.
I don't have to
All right, you guys ready to start? Okay, so the final, I'm just gonna go over some like general info, and then once we're done with general info, I'm gonna go over some like general study suggestions, and then once we're done with those, I'll jump into like some really high level stuff, a simple problem, and then like two harder problems, which are all pretty similar to what you would expect to see on the exam. And then I'm not sure how long that'll take. I'm also like kind of starting to get sick, so we'll see if my voice lasts that long. But yeah, I'll just start with the general final info. It's pretty much the same thing that you would expect from all your midterms. You're going to have 5 sections. And then each section is going to have between 3 to 5 problems each. And then one of these 5 sections will get dropped from your grade. And then for each of the problems, if you do multiple attempts, each one of those attempts will get averaged together. So let's say section 1, problem 3, you do twice, you'll get the score in between the 2 of those attempts. Then, number 2, it's only going to be from chapter 7. So that means basically what you saw in your project and what you're going to be seeing in your homework 7. So that also means no op amps, so only BJTs and MOSFETs. Number 3, material similar to project 2, homework 7. In my opinion, homework 7 doesn't give you enough like basis for BJTs. So if you want to study BJTs on your own, maybe just like pretty traditional stuff. I'll also go over one of those problems at the end here. But you're going to have 2 hours to complete the whole exam. And at the very beginning, you must sign in, just like we did with the midterms. So, bring your red ID, preferably, or your driver's license. Dr. Me will be there. I'm not sure if he'll accept like phone pictures of driver's licenses, so just make sure to have that ready. And then the last but not least, the first 3 questions are going to be MOSFETs. Or I should say, first 3 sections, not first 3 problems. And then the last 2 are going to be BJT. I would say equal complexity on both, so good to study both. Cool. And then, any questions?
For the 5 sections, previously each section has been worth 5 points. Is it going to still be 5 points for the final sections?
I would assume they're all weighted equally.
Okay.
Yeah, I haven't actually checked. I could check real quick if you guys would like. What's up?
Yeah, so you know how you said the one section will be back?
Yeah.
Will that go into effect for the other midterms? Because hasn't been like updated Canvas yet.
I think he has to do it manually, and he's been really busy this semester, so I would assume he would do it at the very end. Yeah.
Can I ask, when will project be created? Will that be done for the final?
Yeah. So my last day to work is today, so I'm trying to have it done today. Otherwise, I'll just be not paid and doing those, which is kind of a bummer. So, yeah, hopefully today.
Just all the ungraded ones you give up 100%.
Yeah, for sure. Last names went out. What's up?
Who is proctoring the final?
It'll be me and Dr. Me.
Okay.
Yeah. So both of us. I'm assuming I'll be in the back. Yeah. What's up?
Are we still gonna have like access to our notes?
Yeah, I think it's exactly the same format. So you'll have your laptop, your notebooks, whatever, calculator. Cool. Next section?
Is it?
One more.
And then for the room, I know it was like 8H something. Is it a different room for the final, right?
I thought it was the same room. I think he said in the announcements. Let me just double check that real fast.
Pretty sure it says the same room in Canvas as well.
Yep, final exam. Oh, it says Adams Humanities 2108. You're right. So,
So that's,
Adams Humanities, I think, is
if anybody has
That way.
271 with a move can compute, that's the same, right?
same room.
Yeah.
Nice. Okay. Sorry, I think you had a question too?
Oh, yeah, sure.
Yes.
That's a good room.
He might have accidentally put down his 270 was.
I'll double check with him on the room. Because, yeah, at some point I think he did say it's going to be in here.
It's a better room.
The other one?
Because you can plug in all your electronics and stuff. Maybe that's why they moved it.
Maybe. I'll double check on the room. Okay. Yep, moving on. Yeah, so general suggestions.
Oh yeah, it says that on 330.
So this is a little bit more technical. The first and most important thing when you're going to be doing the analysis on these problems is when you're doing DC analysis, capacitors are open circuit and AC voltage sources are short circuit.
And presumably DC voltage sources are open circuit as well?
So if you're doing DC analysis, you have to treat the DC voltage sources just
Well,
as like,
voltage sources
Yeah.
are open circuit, so it shouldn't matter, but our small signal
That's
with
the
the
AC one.
Yeah.
would be open.
yeah, that would be your AC, and that would be short circuit. AC voltage sources would be short circuit.
Okay.
Yeah. And we'll go over one problem kind of illustrating.
So that the DC one can still be grounded. Like it still can go through ground.
Yeah, exactly. Cool. Number 2, when you're doing AC analysis, then DC voltage sources and capacitors are both short circuit.
Current sources, DC current sources are open circuit.
Yeah, it would be the opposite of your DC voltage sources. And then general things to know about MOSFETs. Number one, know how to get RO.
That's like the early voltage, right, resistance?
Yep, exactly. Early voltage resistance. And I'll mention that later too. You're gonna need to know GM and AVO, which is your gain. Sometimes AVO is written as like V out divided by V in. Sometimes they won't even say AVO, maybe they'll just say voltage gain. They're looking for AVO. All right, and then number two, you'll also want to know how to get Kn prime, Kp prime, so that's your, Kn prime would be for an NFET, and then a Kp would be for a PFET, so you'll need to know both, PFETs and NFETs. You're going to want to know RDS, and then you'll want to be able to derive like omega and L, or W and L, not omega. Then for BJTs, it's, you know, they're kind of similar devices, same stuff, but different day. Number one, as you mentioned, early effect resistance, RO. So if they tell you to neglect early effect, then that means RO is infinity. I had a fellow master's student accidentally do the opposite of this the other day, and he was telling me a story about that, so I figured I'd put it on here. Yeah, so not zero, infinity, important. Some of the other stuff is be able to find RE.
That's one of the GM.
Let me check that. The question is RE 1 over GM?
Where's that RS? I don't even know.
There's,
GM is 1 over VOV over 2 for MOSFET, and then for the BJT, I have it as IC over VT, VT being the thermal voltage. So you can, you know, substitute IC for the other ones based off of those equations, trading the currents. But let me keep writing down. I think this is VO over VB. So V out over VB being V base. Then you're also going to want to know V out per V sig, which is equivalent to AVO for the whole system. Cool. So those are like general technical comments. Any questions on those? Cool. What?
Could you remind us like why we need to solve for DC first and what we're searching for?
Yeah, good question. So particularly with MOSFETs, I guess with BJTs as well, you need to know bias current.
Oh, that's the big I, those big IC.
Exactly. Yeah, I'm glad you brought that up, because another thing to keep in mind is capital I means DC and then little I means AC. So whenever you're solving for bias current, you're finding big I and big V, and then you solve, then you go and do your AC analysis, and then you find little I, little v. And then voltage gain can be both in DC and in AC, technically. I think, don't quote me on this, your final is just looking for AC gain, not DC gain. but you'll need your DC in order to solve for your AC.
But we're not gonna need R pi for BJTs at all?
You will. I omitted some of the easier stuff.
Okay.
Yeah. Yeah. I think the main thing I was trying to illustrate with this is you're going to need to know gain. And in order to find gain, then you're going to need to be able to solve for a lot of the prior stuff. Cool. All right, moving on then. Let's talk about what model to use and when for each of the devices. And we'll start with the BJT. So there's two models. Does anybody know the name of both of those models?
T and pi?
Yep, exactly. So I'll go ahead and start doing the pi model just to have it on the paper. Cool. And can anyone tell me when you would use the pi model?
There's no resistor at the emitter.
Yep, exactly. Another way of saying that same thing,
Common emitter?
yes. A third way of saying that same thing is if E is grounded. Cool. And then the other model, I think is more useful for your exam. Again, don't quote me on that.
For that model, isn't that supposed to be VBE? For G times VBE is the current going through it?
I think you're right. No, it's V pi for the pi model.
Is that resistor the R final?
Yeah.
Okay,
So it isn't that the same thing as VBE?
Think so. Yeah.
Assuming that the emitter is at ground.
Yes. Yeah.
Yeah, I think it makes sense.
Yeah. Cool. All right. Yep. And then the pi model, or sorry, the T model. All right, and then can anyone tell me when you would want to use the T model instead of the pi model?
Obviously, when there is resistors or voltages somewhere out around our emitter.
Yep, exactly. Yep, so if E is not grounded, Any questions on like how to use these models, when to use these models, how they correlate to gain, anything like that? What's up?
Do you still use the T model, even if he's grounded?
I've never tried.
Okay.
Maybe. I would still use the pi model. Yeah. All right. Yeah, let's move over to the MOSFET models. And I'll try to run through these quicker. Same thing, again, pretty much mirrored devices. Main difference here is that you don't have a resistor between your gate and your source. So that's just a floating voltage, no current flows.
And you, all of these are like AC and DC together, right? Little, or are these the small signal?
I believe these are all for small signal. Yeah.
You don't, when you're finding it out, you don't use these models for finding
Yeah, that's true.
DC.
Yeah, if I'm not mistaken, they're literally called the small signal
Yeah.
model. Yeah. All right. And again, if S is grounded, you'll use this one.
And for RO, you're finding that using the MPC value. Is that what that is?
Yeah, uppercase I. And then VA, I believe, is a product of the transistor.
Yes. That's been.
Okay, and again, you use this if S is not grounded. Cool. Any questions about any of the models before we move on to some practice problems? Sweet. All right, so this is, I would say, like a pretty typical MOSFET problem. Let me make that a little bigger.
Give us a sec to write it down.
Yeah, absolutely. And I'll kind of rewrite the whole thing anyways. Yeah. Okay. So when you first look at this problem, what I do is I always take a look at like all the givens. Sometimes I'll rewrite them just to kind of like solidify that they exist in my mind. And then I'll go searching through my equation sheet, find the one that has like the most of them, and then I'll just start punching numbers. Hopefully it gives me something useful. So looking at this, I can see that we're going to have VGS of 0.7. That's pretty useful, especially if they give us VT, which they do over here, of 0.5. So based off of just those two numbers, I'm going to come over here to my equation sheet, and I'm going to be like, okay, well, we don't have full Kn. We have Kn prime. but I want to use that one equation that everybody's familiar with, so I'll just write it down, which is ID equals 1/2 Kn VGS minus VT.
Shouldn't it be K prime?
No, for this equation, it's just Kn.
Oh, okay. Oh, am I getting K and K prime backwards?
Yeah, it's a little bit confusing. You can think of Kn prime as an incomplete Kn. So, based off of this, I'm like, okay, I don't have Kn. How can I get Kn? So I come back over to my equation sheet, and I know that Kn equals Kn prime times W over L. So coming back to my sheet over here, we have Kn prime. We also have W over L. So I can put this equation into my ID equation. Deriving that gives us 1/2 Kn prime times omega over L times VGS minus VT squared. Then I can just start plugging in values. So that gives me ID equals 1/2 Kn prime is 0.4 times 10 to the negative 3 times omega L, which is 12.5, times VGS, which is 0.7, minus VT, which is 0.5, squared. And did you happen to plug all that in? Yeah, no worries if you have it. I have the answer. But. So.
This is your DC current.
Yep.
So like 0.1 milliamps?
Yep, exactly. So you plug all that stuff in there, and you get
Really small.
0.1 times 10 to the power of negative 3. It is for discrete devices. It is a small number for discrete devices. If you're making a chip with MOSFETs embedded inside of it, that's a lot of current. So really depends on the application. Okay, so I come back, I look at the problem. That's the first thing they asked me, actually. They asked me for ID. So we have that. Good day. Next thing they want is VDS. On the figure, VDS is right here. That's our output voltage. So how would we get that?
VD minus VDS.
Yep.
Just VD. So you take that, you got the voltage source up top, and you just subtract the voltage of that resistor, which is IDRD.
Yep, exactly. So the way we're going to get that is we're going to take VDD, and we're going to subtract the voltage drop across RD. We know that V equals IR, right? So to find the voltage drop across RD, we just need to know ID, which we just solved for here. And we need to know R. Thankfully, they just give us R. Up here, 15 kilo ohms. So if we take our 0.1 times 10 to the power of negative 3, and we multiply that by 15 times 10 to the power of 3 for kilo.
1.5 volts.
Yep, 1.5 volts. And
Subtract that from 2 volts, 0.5 volts.
Yep, exactly. So let me just write that out here. And we know VDD, again, 0.5 volts. Or sorry, it's 2 volts. So 2 minus 1.5 equals 0.5 volts equals VD. Which is the right answer. So that gives us our bias point on the output. We can expect to see 0.5 volts of DC voltage there, even when we're not running any sinusoid through it. And we know that we're going to be biasing with 0.1 milliamps of current through the device. The next thing that they ask for is GM. So I'm going to come over to my sheet over here. I'm going to look at the thing that says GM, and I'm going to see that GM equals ID over VOV divided by 2. Inadvertently, we found VOV already because VOV equals VGS minus VT, which is right here. It's 0.2 volts. So solving for GM, we take our ID, which is 0.1 times 10 to the power of negative 3, divide that by 0.2 divided by 2. So that becomes 0.1.
So 1 sievert.
What's the invert?
1 sievert.
I don't know
No,
what that.
Simon. It's something S. Siemens.
Siemens? Probably. I don't know that term. I'm gonna be honest.
It's what current divided by voltage.
Oh, okay, bet.
Very funny person.
Or if you want to get, I've also heard it called Mohs.
I like that, Mohs. But yeah, it's 0.001 Siemens, I guess. That's the name of a company. That's kind of funny. It's probably named after
I
that.
forget the last name of the guy. And
Oh, is it really?
must have been bullied in school.
Damn. Real. Okay. Yep, milliamps per volt. That's right. So coming back to the problem statement again, it wants to know voltage gain. Voltage gain is defined as V out divided by Vn. So
What is our V out here?
our V out is our VDS. The only reason you can tell that is because they put a little node. You can also tell it based off of the type of amplifier. In the book, I think they go through and they actually define each type of different amplifier, and then you can identify them just by looking at them based off of where the resistor is. I think this is called a common source amplifier. The gain is always going to be negative. So what you can do is you can go through and you can memorize or write down how to get the gain for each one of these amplifiers based off of GM and the resistor, or in the case of other amplifiers, GM and other like configurations of transistors. The way I did it in school was I always just like found it based off of your equations here. Whatever you think is easier. The book recommends memorizing each of the amplifiers.
You can derive it, right?
Right, which is how I used to do it. So I'll show you how the book does it real quick because it's shorter, and then I'll show you how to derive it. And then I'll probably skip the next question. So yeah, let me just show you how the book does it. They use the equation for this type of amplifier not applicable to all amplifiers. AVO equals negative GM times RD. Pretty simple. That's why they have you find GM. You solve that, you get -1 times 15 equals negative 15 volts per volt. Yeah, if you do amplifiers all day, every day, this is a useful skill. Otherwise, I think deriving it is more useful. So I don't think I'll have enough space to do it, but I'll give you what I can. So V out over V in, right? V out is going to be your VDS, again, right here. And your V in is going to be your VGS, down here. Finding those in our equation, you got VGS right here. And then I forgot to write it down fully, but it's based off of when we found our VD here. So VDD minus ID equals VD. Oh. Yep, my bad.
Sounds like a Star Wars master.
Equals VDS. Okay. Kind of cramped in there. Sorry, I know it's hard to read. But here's your VDS, and then your VGS, again, is on the top there. So the connecting bit is ID. So what I would do is I would go and I would solve VDD minus ID, which is this whole mess. You can simplify it a little bit by getting KN and then plugging KN separately. So I'll do that. Oh, you guys in the back can't see that. Is that better? Cool. What's that?
Shouldn't it be the V that's lowercase and the DS that's capitalized?
Yeah, sorry, I'm really bad at being consistent with that.
This is all DC.
This is all DC.
Oh, this is all DC?
Yeah. I think at some point in this problem they tell you that you can assume that the large signal model works for the small signal model or something like that, so this holds.
Yeah, I think that was in the step for the last one. It says
Well, we could use pi model.
You can use pi model. Yeah. Let's do that instead, actually. I think it'll be more applicable for you guys later.
And that would only be for small signals, so we're just...
Right. Yeah, let me just add another page here. Okay, so to do pi model, you're going to have your VGS voltage source coming into here. Thankfully, there's no resistor, so that makes it a little easier. Well, I guess they'd never dive into that in this class, so never mind. Ignore that. This is going to be grounded. You're going to have your current source, your dependent current source.
So this is small signal.
Yep, this is a small signal model.
And we don't have a RO.
I don't think so.
Yeah, I'll double check.
Yeah, we got that lambda equals 0, looks like. Good.
Yeah, there you go. Yeah, so lambda equals 0 implies that you can ignore RO.
Because like RO is 1 over lambda, I believe, something like that, or at least some relation. It is.
Yeah, so RO equals VA over ID, and then VA is 1 over lambda. So VA becomes infinity, RO becomes infinity. Okay, and then on this right-hand section, you're gonna have your RD, and traditionally it would go to VDD, right? But because we're in the small signal model, we can just put it to ground, as we mentioned earlier. Then here is going to be your VDS or Vout. Cool. So, looking at this circuit, we know that our gain is going to be negative because our dependent current source is pointing down, which will pull current through our RD, therefore creating a negative voltage at our node. Once we know that, then we can start writing this out. So VDS equals I guess it would be little, right? So IDS negative IDS because we're reversing it times RD.
What just equals R negative G and VGS.
Yeah, so then we'll swap out IDS with GM VGS times RD. And now that we're in this form, we have V out and we have V in. So we can just do V out. Oh my goodness. V out equals negative GM V in times RD. And we're looking for VO over VI. So V out divided by V in equals minus GM RD, which, if we go back to the other page, is right there. So I'm just going to copy that over here so we can reference it on the same page.
So just making the circuit and like just doing a simple thing can get you kind of the equations for out and in. You can solve.
Exactly. Yeah, so you can either go know every amplifier, put them all on your sheet, know all the equations, or you can derive it with a small signal model. I like doing it this way a little bit more so that we don't have to memorize a bunch of stuff. I'm bad at memorizing. But if you're better at memorizing, maybe that's the route for you. Totally up to you.
Well, we're gonna have a formula sheet, so
Yeah, you'll have a formula sheet and a computer, so maybe,
memorizing just means writing down.
yeah. Up to you. Any questions on this problem before we move on to a BJT example? What's up?
Well, this one will be posted, but could you go back at the end to like someone just use notes?
These ones?
Or, no, the T-model MOSFET.
This? Yeah. Oh yeah, I'm recording this, so you'll have the recording.
Okay.
Yeah.
And this is like the simplest problem we could get for a MOSFET, right? Basically.
The simplest would just be text. There would be no circuit. This would probably be like second most simple you would
We
get.
didn't use any of the complicated stuff. Okay.
What's the complicated stuff?
Like
Well, the DC and like,
we didn't have to use a T model.
yeah,
Yeah, you'll need the T model.
Okay.
Yeah.
I would.
Model T.
I'd more also describe the complicated stuff as that this one has very simple DC circuit to analyze.
Yeah.
Versus the
Yeah, it didn't have a biasing.
Yeah, so the next one I was going to show you was this one.
yeah.
Similar to what you had on your project, right? We only have 30 minutes. I don't think we'll have enough time to do this one. And I think it's less important than the BJT one because it's a MOSFET. You don't have current going through your gate.
Yeah.
So the other one I was going to show you, it's basically the same thing, but with a BJT.
It's the exact same thing, except you just open and do certain openings and things
Well,
like that, right?
we're not. There isn't a capacitor on our VSync with
Yeah.
this version.
Ooh.
Yeah, that's a little bit different.
Well, it's a BJT though.
Yes, you're going to have current.
Is there gonna be any tricky stuff like it's gonna be in cutoff, or can we assume it's all gonna be in saturation for this test?
Dude, he gave us an early voltage on the last midterm, and it was in triode, and we didn't need to use it. I was like, this guy gave us an early voltage,
Like, should we?
and it's in triode.
Should we assume saturation and just jump straight into solving it, or should we do our checks first for the test?
I'm going to be 100% honest. I don't remember. Yeah.
Yeah.
But if it's not, then I'm.
Yeah. You have a little bit more time. Instead of an hour and 15 minutes, you have 2 hours, right?
Well, it would also be safe to assume that we're in
I think he mentioned that we're chilling. Like, we're gonna be
saturation because if it's not in saturation, we don't have gain. We're not gonna have gain.
I remember asking about that. I think he mentioned that.
That's a
we're
good point.
Be fine.
Yeah.
It's all gonna be in saturation.
What's up?
For the homework due on Sunday, I mean, typically you usually post the solutions like prior. Are you gonna be doing that this time?
Yeah, right before the exam. He hasn't mentioned it, and you have it's due on Sunday, right? And then your exam's on the 18th. So there's 4 days.
No, let's do this Sunday.
Yeah, the homework's due on Sunday, but then your final is on the
Yeah, we have
18th.
4 days.
So you have 4 days between
That's
those
right.
those things happening.
Yeah.
So I wouldn't expect him to have me post those early. Right now I have them scheduled to release on the morning of the 15th at 9 a.m. or something like that. Yeah. Okay.
So this example.
Yeah, so let's start with this. Again, I think there was not enough BJT stuff on the homework, so this is one of the ones that was on your homework and I think is relevant.
And I assume those are infinite capacitors.
Yes. Yeah, you can't see it too well, but they do have little infinite symbols. So they're infinite capacitors, ideal capacitors. Your beta is going to be 100. That's very typical, 100, 101, something like that, at least for these classes. They're going to be wanting us to solve RE to establish a DC emitter current of 0.2 milliamps. So if we're going to be doing DC analysis, what do we do with those capacitors?
They become open circuits.
Cut off everything after that.
Yep, exactly. open circuits. So I'm just gonna scribble them out for right now. Assume they're not there. That means that our RE that we're assuming is all going to be going through RE. Or sorry, all of the IE is going to be going through RE. Similarly to the capacitors, what do we do with VSIG? Yep, exactly, short circuit. So I'm just going to draw a line straight through it to represent that it's a short circuit. And now we basically have everything that we need to do our DC analysis. Really simple. If you look at it like this, you kind of just ignore everything happening up here and you do a loop. So you assume that you have, sorry, that's DC, IE here. You assume that you have IB here. So the voltage at the base of your BJT here is going to be 0 because you have ground minus IB times R sig. And then your voltage at the emitter will simply be minus 0.7. You just assume that 0.7. And then the voltage drop across your resistor, RE, is going to be IE times RE.
You're adding that?
I'm adding that because of how the current is flowing.
So it's going from like a.
Wouldn't we only be adding it if it was flowing up? Because like so our current is going with us across our sig, and then we're also going with it in the loop.
Yeah, you got a good point. Okay, there we go. And then you're gonna subtract your 3 volts.
Where's our loop again? Is it?
And that equals 0 volts.
Equals 0 volts. Yeah, good question. Your loop
It's
is
just there.
here.
Got it. Okay.
Yep.
Thank you.
Yep, and then all of that equals 0 volts because you're doing a loop. Okay, so we have RE, right? No, we don't. We're trying to find RE. We have IE,
The point.
and we have beta, which means that we have IB, and we have R sig. We're solving for RE.
Yeah.
So you just plug, solve, get RE. I'm just going to pull up the answers to try and speed this up a little. Yep. So you plug all that in. Oh, that's interesting. The answer sheet actually has the beta as 101 instead of 100. So
Well, no. Isn't it beta's relationship? So you have beta plus 1 is the relationship between
Oh, yeah.
IE and IB.
yeah, you're totally right.
It is IC to IC.
Yeah.
It says IE over beta plus 1 is beta. IB.
Yeah.
No, IB is beta plus
Yeah.
IE equals beta plus 1 times IB.
Got it. Okay.
No, alpha's like near 1. It's beta divided by beta plus 1.
Yeah. So basically going off of what he said, your IE over beta plus 1 is going to give you your equation for IB. Solving that a little bit further just gives you RE equals 11.5 kilo ohms. Once you plug everything in. And then you're done with step A. Moving on to step B, they want to know RC to establish the DC collector voltage of about 0.5 volts. So that is looking for the voltage at this node. And they want that to be 0.5 volts, right? So if you know your emitter current, which we do, and you have the equation to calculate for the collector current, which in theory we do if it's on your note sheet, then we know what voltage is going to be at the collector, which is going to be 0.5, and we know the voltage on the other side of that resistor, which is 3.
So it's 3 minus 0.5 equals IC times RC.
Yeah, 3 minus 0.5 equals RC times IC, and we're looking for RC. So coming over to my note sheet,
It's alpha times.
I don't think we have alpha yet. So let me define alpha. A equals beta over beta plus 1. And then we know that IC equals
Point.
A alpha times IE. And we know IE, which is 0.2 milliamps. So plugging that in, we get 2.5 equals RC times beta over beta plus 1 times, I'll just do IE. And then taking that, you get 2.5 divided by 100 divided by 101 times 0.2 times 10 to the power of negative 3 equals RC.
4.625.
Uh,
Or am I making error?
so they say about, so they're expecting you to round that to 12.5.
What was the real answer?
The answer from the book is 12.5. The answer you gave was 12.65?
Yeah, I might.
That's not the same thing.
It's not the same thing, but let me
I
zoom.
assume that they did rounding on the. So we have 100
Yeah.
divided by 101. They rounded that down to
Maybe they want you to.
99.99.
Yeah, they say about 0.5 volts. This is the hand wavy part of like amplifier design, because of manufacturing tolerances, you're never going to get actually 0.5 volts. So they're like about 0.5 volts. So your RC will be approximately 12.5 kilo ohms.
Approximate whole flash test.
Yeah.
I'm nervous.
Well, it's multiple choice, so.
It's multiple
Oh,
choice.
yeah, that's
They'll give
right.
you something.
Yeah.
Okay. Then the very last thing is they want you to find the gain. They want you to draw the small circuit equivalent model, and then they want you to find the overall voltage gain for the circuit.
High model.
No.
Well, it is grounded.
It is not grounded.
But we got
Well,
our.
it is grounded.
Oh, yeah,
It
you're
is
right.
grounded when the capacitors exist.
Yep.
Oh my gosh.
Yep. Yeah, my bad. I already crossed them out. Let me create a new page here. open up the circuit model again so we can have a fresh look. And in this model, doing AC analysis, we're switching over. So this is short-circuited, this is short-circuited, and we can pretty much ignore RE.
As
Well-
you're parallel to a grounded, and the
Yeah.
V minus becomes a ground.
Yeah,
So you're parallel to ground.
yeah, so it's a 0 ohm resistor in parallel with an infinite ohm resistor. I think, yeah, so in the answer sheet they have that there, but it doesn't matter because it's bypassed entirely. Okay, so let's go ahead and draw that model. The V-sig is just V-sig, right?
Yep.
So you're going to have a plus minus, and then that's going to be grounded. You're going to have your R-sig still. Then that's going to go into your pi model. So you're going to have R pi here. And I'll just leave everything grounded to make it a little bit easier to look at. You're going to have plus or minus V pi across that R pi resistor. And then your dependent current source is going to be GM V pi. Then we're going to come and we're going to look. We're going to see that we have our RC, but the very top of here is going to be grounded.
Are we gonna have an R early voltage?
If they don't mention it, it's probably not working.
Yeah.
There's nothing to go off of.
Yeah, if there's nothing to go off of, if you literally can't solve for it, just assume you neglect
Assume it's
early voltage. Yeah. Which you can't, for the record, you can't solve for it here. We don't have all the information. And then thankfully they just give us VO here. Yep, V out. You don't have to go translating. All right. So now that we have our small signal model, then we can go and start deriving the voltage gain, the small signal voltage gain.
What would
Tip-
be in for this one? What's like the in?
Vn would be Vsig.
yeah,
Still?
Yeah, Vsig. Yeah. Because you're going to have like some other kind of amplifier on the left-hand side of this circuit,
Oh.
which they then simplify to be a voltage source, a AC voltage source. So you want to see like the output of this amplifier getting fed into now the one we're analyzing here. What is that going to affect?
Go ahead.
Yeah.
So we have basically voltage divider and a resistor in parallel.
Yep. Yeah, you got two resistors in parallel. So to simplify that, you can just combine those two.
What do with that?
You can't just combine those two. I don't like doing Thevenins. Yeah, I would just combine these two, and then I would just do your voltage divider here to simplify it, and then you can combine those two systems together, and then you can make it work. So the first thing you want to do here is you want to find V pi in terms of Vsig, right? Because in my mind, it's easiest to keep it in terms of volts per volt throughout the whole system. So V pi equals
R pi
Yep.
divided by R sig plus R pi times V sig.
Yep. Yeah, what is R pi is a good question.
That's the one that like makes beta really small. Or that makes the current, the
like-
base really small, right?
Yeah, exactly, because it's a big resistor. It's in this one, or sorry, the equation for it is beta divided by GM.
Oh, good to know.
Did we ever calculate GM?
No, we'll get there. No, we haven't calculated GM yet. So I'm going to derive the volts per volt amplification equation. Then we can find each one of the things that feeds into it backwards, but it works.
I'm saying like,
Doing the right-hand side of this, we can kind of see, again, we're going to end up with a negative gain because the current source is pointing down. Our current through the load and through our RC is going to come up. Just kind of with that in the top of our mind, we can do V equals IR, right? And we want to know V out, so we're going to say V out equals GM times V pi.
Well, negative GM.
Yeah, sorry, negative GM times V pi times RC in parallel with RL. And then I'm just going to take these two and mash them together before we solve, which gives us V out equals negative GM times R pi divided by R sig plus R pi times V sig times RC in parallel with RL. And from here, you want to get V sig on the other side because you want VO be over VI.
We can just divide by B sig, it's on.
Yep. Yeah, so you can remove these parentheses here, have them all be multiplied together.
Oh, you're just modeling the equation to find the gain from it?
Yeah. I guess since it's multiple choice for you guys, it's always numeric, but in a lot of classes, they want you to find the whole equation.
Yeah.
So this way you have the equation, you can use it later for other purposes if you're doing a project, whatever. V out divided by V sig equals, what is it? AV, AO, voltage gain. Yeah, AV equals negative GM R pi divided by R sig plus R pi times RC in parallel with RL. Yeah.
what would we get?
What's up?
We still need to find GM, so what would we get?
Yeah, good question. So we need to find GM.
The School of Physical Therapy, that is
Kind
a
of need to
great
go
place
back
to
to
get
our-
hands-on experience. It basically has a bunch of different.
Yeah, so the equation for this is pretty simple. GM equals IC divided by VT. Somewhere in your notes you should have VT equals 0.025. I don't think I've ever seen an equation at this school or a problem at this school where they use VT as something other than 0 or 0.025.
Volts? Is that just volts?
Yeah, volts. So just have that down somewhere. It makes finding GM really easy once you have IC. If I'm not mistaken, earlier in the problem, we found IC. Kind of. We used it.
Well, we know IC is our beta divided by beta times 1 of our IE, which we know to be 0.2 milliamps.
Yep, exactly. I'm just going to copy that over here. So GM equals beta divided by beta plus 1 times IE divided by 0.025. Our IE was, I'm not going to have enough room to write this, but GM equals 100 divided by 101 times 0.2 times 10 to the power of negative 3 divided by 0.025, which equals they rounded.
Something.
Yeah, they rounded. They just assumed the 100 over 101 is 1. So you're dividing 0.2 milliamps by
So like it's
Yeah.
around
E milliamps, yeah.
milliamps.
Milliamps per volt.
Or
Yeah. What's up?
I'm assuming, because on the low end, we have 15 to 25 problems in total that like, it's gonna be combined like multiple, okay, because like doing 15 to 25 of these in 2 hours will not be possible.
Yeah, that'd be insane. You can very well assume that one section is one of these problems, and then one problem in that section would be your A, one problem would be your B.
Okay.
Yep. I think that was one of the issues I actually had with this exam when I first did it, was they didn't tell you that each section was one problem, and you assume that the numbers from one part goes to the next part, which goes to the next part. Yeah. So in each section, assume that your numbers from the previous problem in that section applies to the next part.
So take note of all your values and kind of leave them and you come back to them.
Yeah.
Yes. Yeah.
Exceptions to that on the last.
Yeah, there was a few.
I think there was.
yeah, but the few exceptions were like kind of they were really easy problems.
It was also, yeah, it was obvious when there was, but.
Yeah. In this one, I rewrote it a little bit to try and make it more obvious. You just always assume
Okay.
that one section is one problem.
Thank you.
Yeah.
Should do that.
Yeah, so coming back to this, we have GM now. Did we solve for IPi? Oh, RPi is just based off of GM and beta.
Yeah.
So we have RPi. We have our C already from the previous section. We have our L from the previous section. And
We have
our sig was
is
given. Our pi we derived. So you plug all of that stuff in to here, and you get. I'm just gonna write this as AV to make it a little bit more clean. Equals. Oh, you guys can't see that. Shit.
There you
I still think the people in the back can't see it. Let me just add another page. Okay, so AV equals negative 12.5 divided by 12.5 plus 5 times 8 times 12.5 in parallel with 10. AV equals negative 31.7 volts per volt.
go. Nice. That's pretty big.
Yeah, it's good amps. Good amplification. Any questions?
Do you think we're going to have an exam, one of the questions on the exam require us to use a T model?
Yes.
Okay.
Yeah. Yeah.
Is it gonna be a MOSFET or a UJT?
I can't tell you that.
What are the exact values and how can I solve it?
Yeah.
Do you understand the VT equals 0.025?
It's somewhere in the book. It's thermal voltage. It fluctuates as the temperature of the MOSFET goes up and down.
It's a weird temperature thing, right?
Yeah.
Weird.
You can just always assume it's 0.025.
I remember when we did
this,
the
because
current
it like
equation,
doesn't change. But
I use it too, where it's like it's like VBE over VT, it's like E to the VBE over VT when we did the current. We use it there too, it's just a
Probably
constant.
hasn't changed.
I would just stays the same.
I would
I think I got, I might have zoned out or something, but, where'd you get the 0?
I got it.
0.7, yeah, you just always assume the voltage drop across your VT is 0.7 unless they tell you otherwise.
No class today.
You added that or you?
Oh, yeah.
You did.
Pretty sure I subtracted.
It's like, yeah.
Yeah, subtracted.
Alright, thank you.
On the very first midterm, there was a problem that I don't think was right, and he like talked about it. And I don't know if he said he was going to give out the 5 points, regardless of whether you got it right or not. Did he ever say if he was going to do that? I don't remember.
If you didn't mention it, send me an email and I'll follow up with it.
Okay, thank you.
Just tell me which problem it is. Yeah, the other problem is going to be this one. It's in your homework. It's number 33. It's the same thing, but for a MOSFET. I think it's a little bit easier. But yeah, you'll do it on your homework, and then the solutions will be posted on Monday morning, so you can go over
And
it.
then will the solutions this time like show like how to go in depth, or is it just like the answers?
It should be the same as before, so it kind of gives you like most of the steps. Yeah.
When I'm taking the FE and B,
Don't ask me hard questions. I don't know. Maybe eventually. Yeah. We'll see how desperate I am for a job. Yeah.
Is the exam open notes though, or is it just a formula sheet?
Yeah. All open notes. Yeah. I like having a formula sheet because it gives you all of your information in one condensed place. You know.
Okay.
Yeah.
Thank you.
Of course.
My question was on the formula sheet. I saw that you're referencing one. Is it possible for you to share it, or is it like you actually hand wrote it yourself?
I hand wrote it. I can share it. If you can read my handwriting here, then you'll be able to read it there.
Okay, yeah, thank you so much.
Yeah. Of course.
And the project, what is that going to be graded?
Trying to get it done by today. Trying to.
Okay, and this is going to be posted online video?
Yeah, the video will be posted online, and I don't know how long it's going to take him to do that. Yeah.
So I just have a quick thing that happened. Okay, so when I turned in the project.